Hello, everyone. My name is Stephen Dubben, and my project today is mapping strain variation in SRF cavities using image analysis. I'd like to thank mentors Dr. Lee and Shreyas Balachandran, and I'd also like to thank Abigail Williams and Brandon Schmidt. So figure 2 represents what a niobium cavity actually looks like, and figure 1 is a cross-section of that niobium cavity complete with hardness tests, and this is the primary thing that we will be discussing in this presentation. So superconducting radio frequency cavities of Niobium are used because they achieve very high accelerating gradients, and we seek to further improve their performance by understanding their microstructure. So these cavities are formed from flat sheets of Niobium, and they are curved to produce these cavity walls, and this introduces strain in the Niobium. And what we want to do is understand the strain so we can correlate strain with hardness testing. Because hardness testing is much easier to do than strain testing. And we will be using an image analysis software to extract our hardness data from diamond hardness indents and be able to combine many, many hardness tests onto a single image. So the original image is taken with a light microscope, a DSX, and I first import it into ImageJ. I then convert it to binary, analyze the particles, and then run some data collection software. So I run a macro to convert the indent dimensions to hardness values. And what this basically does is the softer the metal, whenever you use the diamond drill, the larger the hole will be. So that's how that program correlates hardness with the indents. And then I also collect the centroid coordinates of the hardness tests. And then I wrote a MagLab script to combine the centroid values with the hardness values. And so we have on our x-axis the width and y-axis the height of our piece of metal. We also have our hardness values with a scale. And on the left side, the iris-oriented side of the niobium has a higher strain. And on the right side, the equator-oriented has a lower strain. So in conclusion, this process is a proof of concept that ImageJ and MagLab can be used to quickly and efficiently quantify images and show the results of the hardness test in a clear, concise way. It can also show that many, many hardness tests can be compiled on a singular image. To continue this project, there will be 4 pieces of metal about 10 centimeters long, divided into multiple sections with 500 plus hardness tests per section. And so it was very important that our software is able to handle a very large amount of data. And a potential change we could have is we don't have to specifically use MagLab, since a MagLab license is pretty expensive. We could use a free language such as Python to accomplish this as well. But anyway, thank you for listening and thank you for your time.